So, hello everybody, and welcome to the channel. Today we're going to be live streaming, and we're going to be running what we call the log for integration tests. Give me 1 second. Sweet. So, let me see. Stats. So, everybody, welcome to the live stream once again. And today we're going to be continuing what we've been doing now for a couple of days, which we're following Luca's Palmieri's on on his book From Zero to One. Zero to Production in Rust, an opinionated introduction to backend development, in which we're basically covering his take on how you should build like backends for Rust. And we're taking it here as a journey, more like learning a couple of new things, like taking this journey together as we because there are a couple of things like Rust. I believe Rust is one of the most powerful programming languages that are coming out or that have come out in the recent years, and we have to learn about it because probably there are going to be a lot of products that we build that Rust is going to be involved, and we just want to learn enough for us to be good at it, not like the best or the experts. And we're here right now checking on chapter 4.5.11 for integration tests. I'm going to be sharing the GitHub repo in the description soon, so don't hesitate to check it out. And today we I'm just gonna read because the yesterday we so yesterday we were on chapter on we left here like 4.5.11, and it says we're not just cleaning up for aesthetic readability reasons. We're moving those two functions to the zero to prod library to make them available to our test suite. As a rule of thumb, everything we use in our application should be reflected in our integration tests. Structured logging, in particular, can significantly speed up our debugging when integration test fails. We might not have to attach a debugger. More often than not, the logs can tell us where something went wrong. It is also a good benchmark. If you cannot debug it from logs, imagine how difficult would it be to debug in production. Let's change our spawn app helper function to take care of initializing our tracing stack. So one of the most interesting things that are going on in here is that generally, and he has a really good point. When you're debugging an app and in production, especially in production, you have no visibility to it. I do know that you have like Visual Studio and C# code that you can remotely debug a code, which is awesome. But that's really like not practical when you are in heavy production environments when you're having a lot of requests. And literally logs are probably one of the few sources of truth that you have for you to actually understand. Imagine you're having like I'm not talking about millions of users. I'm only talking about like you can start having problems with a lot of problems with like 100. I would say like 1,000 users, 1,000 concurrent users using your application. If something goes wrong, you have really no idea. You will need a lot of stuff for you to help you diagnose the issue because everything can fail. Like literally everything can fail, and it becomes awful when you have to move extremely fast. You're building a feature, and then this comes up, and you have to patch it, work yourself through it, and the very first thing you have to do is to understand and identify the problem. Like if you cannot identify it, then you won't be able to do anything because you don't know what problem to solve, and you can just monkey patch blindly because it won't work. So we stay here, and we're going to be adding. So the problem that we did on the configuration yesterday was that the init subscriber should only be called once, but it's being invoked by all of our tests. And we're going to be using the one cell to rectify it. And I'm going to come here. Okay, give me a second. was working outside, so I love working on open areas versus like being closed into a certain place. I'm here because this is the best place. I'm out of my room. Okay, now I'm gonna add cargo add one cell and install that package. Remember that all your packages are inside cargo.toml. And cargo add usually you had to install another crate that would handle it for you. But in recent versions of Rust, I think it was like 1.63 or 1.64. It added the ability for you to actually do it. It was I don't know why it was never there, especially people that were involved in the web environment and they know. So our next step, according to the book, is to use the one cell sync lazy and specify it. So here it says something really important. Even though we never refer to tracing after its initialization, we could have used std sync once with this call once method. Unfortunately, as soon as the requirements change, you need to use it after initialization. You end up reaching for standard sync one cell, which is not stable yet. One cell covers both use cases. This seemed like a great opportunity to introduce useful credit into your toolkit. And here it is, lazy new, static tracing, lazy new, let's subscriber, and lazy force. The first time initialize invoke, the code and tracing is executed. All other invocation will skip execution. So it's more like a some sort of singleton that you're gonna be working here, and like literally, it's going to skip if it doesn't work. Dun, 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 dun. So here we're gonna come to the health check. I had it instructed here, and we're gonna include use one cell lazy. We're gonna come down here, and we're gonna add a static tracing. Returns let subscriber equals get subscriber test. Okay, I think we have it here. Here it is. So we're gonna come extract it, factor it, and return this. And now we're gonna be using it like this. Tracing, but no, it's not like that. Oh, okay. So we have to do it like this. Lazy, force, and we pass the reference of tracing. It's interesting. This is interesting. So this is like a way for us to create a singleton pattern within Rust, I believe. And actually I like this. This is like a good pattern to continue to use. Cargo test, and let us run cargo test to see if it's actually working. And we're waiting for our test, and we can continue reading in here. So it says it should go green again, and the output is very noisy. We have several log lines coming out of each test case. We want our tracing instrumentation. By the way, I'm so sorry about this. Let me just increase the size. Okay, that works. We want our tracing instrumentation to be exercised in every test, but we do not want to look at those logs every time we run our test suite. Super true. Cargo test solves the very same problem from print line print statements. By default, it swallows everything that is printed to console. You can explicitly opt in to look at those print statements using cargo test. No capture. We need an equivalent strategy for our tracing instrumentation. Let's add a new parameter to get subscriber to allow customization of what sync logs should be written to. Oh, here's something really interesting. I've never heard about a higher rank trade bound. This weird syntax is a higher rank trade bound. It basically means that sync implements the make writer trait for all choices of the lifetime parameter. A. Da, 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 for more details. Uh-huh. Okay, let us write it. See if we don't run into any issues while it's compiling. And here we go. So we have, no, it's in this get subscriber, right, method. From here, 12. Oh, I misspelled telemetry. Yeah, I misspelled it. Telemetry. Okay. Yes. Telemetry. Telemetry. I I strongly recommend for everybody to download the spell checker Visual Studio extension code, which believe me, it solves a lot of problems like this one. So we're gonna come here to the telemetry one, and here's the get subscriber method function, and we're skipping the unfilter, and we're adding the sync value sync. So does it come from the future? Oh, is we need to use tracing subscriber later and filter registry and then sync. No, no, no. Format FNT make writer. Okay, sync. Mm-hmm. And we have to return increment subscriber plus sync plus send. And then we have to specify where. Sync. Now this is like a very strange syntax. A make writer. A plus send plus sync plus static. I'm gonna add it here. This is really strange. But the thing is that it is actually telling me to import grid sync, but I have no idea. I think I should use standard. It's probably gonna complain if it's not the thing that I'm looking for. Okay, cargo types. No, no, it's gonna break because I already added another parameter. VN formatting layer new name. Oh, okay. I think this one is gonna complain. Output the formatted spans to standard out. So I'm gonna comment that one. I'm gonna add it here as sync. Make writer. Okay. All right. Here we go. Telemetry file. Somebody working. We can then adjust our main function to use standard out. And I'll come here, main.rs. Standard, yep, that was the one. So we're gonna come here and add a standard IO std out. Sweet. Expected struct sync and found function items standard out. Function defined here. What you saying?
expected a function closure found in sync. The trade function is not implemented for sync. Jesus Christ. Should blow up. Make writer. Okay, I think the book didn't specify how should we use sync, self and write, and then write buffer and then wrap. But I don't know if by omitting this, we actually specify something different. Is it? It is. It's like checking a struct. Considering importing one of these items, feature sync, small IO, futures, async standard, and those are all crates that I installed on my own. Like none of them were actually required into our candidates. It should definitely be standard IO sync. The problem is that I don't know how can we operate with this one. Because the guest card says like it's this is what it says in the book. Like literally left formatting layer, boolean formatting layer, new name and sync. Then standard IO, standard out. In our test suite, we will choose to sync dynamically according to an environment variable test log. stdio sync. IO standard out. Jesus. What should we do here? Okay. Uh-huh. Sync for A, make writers send sync static. Thing is that this doesn't tell me a lot. So only tells me example. It's IO sync the write buffer on wrap. That's it. So I think let me start with higher rank trade bound. We try to naively sugar this code and so higher rank trade bounds. Rust function traits are a little bit magic. Let me see where's the trade, where's the trade, where's the trade, where fn. For instance, we can write the following code. Struct data func f, implement f closure f or f function and u8, u16. Do it make. If we try to naively sugar this code in the same way that we did in the lifetime section, we'll run into some trouble. Note, nb data.0 and it's not a valid syntax. Dude, at my brain right now, it's like hurting.
Where's the trait? By the way, where's the trait in here? Function traits. I think we should start by searching for function traits. Oh, wait. Oh, here it is. Close block. The three traits defined as follows. Pop trait, FN args, FN mute args, extern Roscoe, FN call, and self args args. Jesus Christ. Pop trait, FN once, extern Roscoe, FN call mute, and mute self args args. It's a super trait. Ross doesn't have inheritance. Begin to find this trait. Jesus. Ross doesn't have inheritance, but you can define trait. Is being a superset of another trait. For example, trait person. Person is a super trait of student. Implementing student requires you to also implement person. Trait student derives. It's kind of interesting that in the book it actually says that subtraits are actually the combination of traits, not the other way around. I would say like a mega trait as the combination that has all those traits. Like a subtrait would be person. But I kind of understand why is it saying that because it's actually kind of like deriving from person. If we try to see it like in a OOP manner. I know that in Rust, like one of the biggest hurdles and the thing that you should avoid is like literally trying to think as a with an OOP mindset. That's like completely wrong. And function computer science student greeting student. Yeah, we always need to specify that's computer science student. Format. My name is favorite language is. Here's how you combine the traits. This is how you extend them. Got it. But what I don't get is that what the hell is a. So right now, function args is actually inheriting from function mute args. So this is a subtrait from function main. But I don't understand here this one. Let me see if I can find it. We need to work towards writing a function that can accept and work with closures, taking variables, numbers, and type arguments. Let me see if this is what we're looking for. I'm skimming through everything here because I think I need to stop to actually learn, study a little bit more about this because Jesus Christ. Let's see. In this post, I'm going to work towards writing a function that connects up and work with closures, taking variable numbers and types of arguments. On the way, I'll look at trait families and a way to avoid overlapping implementations. As a refresher, when we want to pass functions around in Rust, we normally resort to using the function traits. As a refresher, when we want to pass functions around in Rust, we normally resort to using the function traits, fn, fn and fn1. Okay, so those three are actually traits. The function type, fn foo, foo as param, and bar as a return tag can also be used, but it is decidedly less powerful. I'm not particularly concerned about the distinction between those traits here. The Rust book covers that. Yeah, I know about closures. I know about closures. Anything that implements a function also implements function mute and function once. Anything that's function mute also implements function once. So basically, function once is the one that's kind of like the parent, and the one that are the derivative. Closures and functions automatically implement the traits based on how they use the variables that they close over. If you're writing something that can be handed a closure, it's often preferable to accept anything that implements the fn once trait if you're able. Falling back to fn mute if you need to call the function more than once, or fn if you can't mutate things. What I get is, why do you need to call fn? I mean, if fn implements both fn mute and fn once, doesn't it mean that you are actually passing a mutable function to function? And why does it say in here, like, if you need to call the function more than once, or fn if you can't mutate things? It gives as much flexibility to the person defining the function as possible. Anyway, a very simple example which takes advantage of a function trait might look like this. Fn run twice, and then f, and we get f as fn, use size, use size. Okay, I know, I understand why this would be a trait, but the question becomes, why wouldn't this be thin in here? The then keyword, the dying, I don't know how would you spell it. Like, keyword is used to highlight that calls to methods on the associated trait are dynamically dispatched. Die. I think it should say dying, dynamically dispatched. At runtime. To use a trait, this object it must be object safe. Unlike generic parameters or implement trait, the compiler does not know the concrete type that is being passed. That is, the type has been erased. Type erasure. It is the load time process by which explicit type annotation are removed from a program where it is executed at runtime. Operational semantics that do not require programs to be accompanied by type are called type erasure semantics. Protection principle, ensuring that the runtime user does not become type information. Jesus Christ. This is like way low stuff. That is the type of reason. At runtime, remember, I have no computer science knowledge, and I'm literally like getting a reverse degree by rereading all this information. At runtime, when a method needs to be called in dying trait, the v table consolidated at the function pointer, and then the function pointer is called. Okay, what is the v table? Okay, virtual table. As such, that means in like that has been erased. As such, a dying trait reference contains two pointers. One pointer goes to the data, an instance of a struct. The pointer goes to a map of method call names to function pointers. A map of method call names to function pointers. At runtime, when a method needs to be called on the line tree, the VTable is consoled to get a function pointer and the function pointer call. Okay, so what it's basically saying is that the dyne tree, like you would have like some sort of mapper. I would, if I need to write it out, I would write like a JSON. Is that I'm gonna write like a JSON. I know that this is not the correct implementation or the right implementation, but I think we can actually get like really close to it. I think it's something like this, like function name here, and then it would be something like this. No, because you don't store the function by itself. And one point was the data map of method call names to function pointers. So it's basically will tell you about functioning here, and then it will be the pointer to the function that you will be able to execute, and 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 you will be able to pointer to the memory that holds the function which is basically an instruction set that you will be able to execute. Got it. Got it. Got it. On methods associated trade argument. We're going to store the different types of data in each cell and still have a vector. And however, sometimes we want our library user to be able to extend the set of types that are valid in a particular situation. To show how we might achieve these, we'll create an example graphical user interface tool that iterates. Is this in the book? Oh, so 17. It's chapter 17. Okay. Yep, I didn't get to read this far actually. I mean, I skimmed through this all of these because like I didn't pay too much attention. Oh my god, it's incredible how much reading you have to do in order for you to actually get to understand this. Like literally this. You wouldn't get anything because in here, the question that I had was why wouldn't I implement the dyne trait, dyne keyword in here if it's an actual function, and coming in here, then it sends me to the trait object. I just love this. In chapter 8, we mentioned that one limitation of vectors is that they can store elements of only one type. We created a workaround in listing A9 where we defined spreadsheet cell enum that had variants to hold integer text. This meant we could store different types of data in each cell and still have a vector represented in a row of cells. They're a perfectly good solution where our interchangeable items are a fixed set of types that we know when our code is compiled. However, sometimes we want our library user to be able to extend the set of types that are valid in a particular situation. To show how we might achieve this, we'll create an example, graphical user interface, GUI, that tool that iterates through a list of items, calling a draw method on each one to draw it to the screen. A common technique for GUI tools. We'll create a library crate called GUI that contains the structure of a GUI library. This crate might include some types for people to use, such as button or text field. In addition, GUI users will want to create their own types that can be drawn. For instance, one programmer might add an image and another might add a select box. Got it. We won't implement a fully fledged GUI library for this example, but we'll show how the pieces would fit together. At the time of writing the library, we can't know and define all the types other programmers might want to create. But we do know that GUI needs to keep track of many values of different types, and it needs to call a draw method on each of these differently type values. It doesn't need to know exactly what will happen when we call the draw method. Is that the value will have that method available for us to call. To do this in a language with inheritance, we might define a class named component. It has a method named draw in it. The other classes, such as image and select box, would inherit from component. It doesn't inherit the draw method. This is absolutely true. They could each override the draw method to define their own custom behavior, but the framework could treat all the types as if they were component instances and call draw. Okay, we got that. But because Ross doesn't have inheritance, we need another way to structure the UI library to allow users to extend it with new types. Okay, defining a trait for common behavior, which is basically what traits can be used for. To implement the behavior one UI to have, we'll define a trait named draw that will have one method named draw. Then we can define a vector that takes a trait object. A trait object points to both an instance of a type implementing our specified trait and a table used to look up trait methods on that time at runtime. We create a trait object by specifying some sort of pointer, such as a and reference or a box matter pointer, then the dyn keyword, and then specifying the relevant trait. We'll talk about the recent trait objects when we use a pointer in chapter 19, section dynamically sized types, and the size trait. These are kind of the things that you end up like reading and rereading and rereading and rereading and rereading, and at first it wouldn't make sense because you have practically no use of them. Like as I've said in other videos, learned I come from learning early PHP and then JavaScript and then proper JavaScript and then C sharp and maybe you can add some flavor to Ruby and Python, but I've never been this low. So there are a lot of concepts that I never got to know and understand, like smart pointers and the heap, the stack, because I never got to use them. And I was able to build like fully fledged applications without actually knowing them because all those languages abstract all that knowledge. So we create a trait object with specifying some sort of pointer, and we create a trait object with specifying some sort of pointer, such as and reference or a box mark pointer, then the dyn keyword, and then specifying the relevant trait. And then that we'll talk about the recent trait objects must use a pointer, chapter 19. Sorry, in the section dynamically sized types and the size trait. We can use we've mentioned that in Rust. We refrain from calling structs and enums objects to distinguish them from other language objects. In the struct or enum, the data in the struct fields and the behavior and implementation blocks are separated. Whereas in our language, the data and behavior are combined in one constant is often labeled an object, which is completely makes sense. However, trait objects are more like objects in other languages in the sense that they combine data and behavior. But trait objects differ from traditional objects in that we can't add data to an object. Trait objects aren't as generally useful as objects in our languages. Their specific purpose is to allow abstraction across common behavior. Okay, so we got a trait called draw, function draw, and self. It actually has a reference for itself. Then this syntax should look familiar from our discussion how to define traits in chapter 10. Let's go some new syntax. Lesson 16.4 defines struct named screen that holds a vector named component. This vector of type box dyn draw, which is a trait object, sets stand in for any type inside box and implements the draw trait. 16.4 definition of script holding a picture of trait object implement the draw trait. On the screen struct, we'll define a method named run that will call the draw method on each of its components, as shown in listing 16.17.5. And We got the library.rs, and it says from components of components.iter, component.draw. This works differently from defining struct, and we have it here. This works differently from defining a struct that uses a generic type parameter with trait bounds. Generic type parameter can only be substituted with one concrete type at a time, whereas trait objects allow for multiple concrete types to fill in for the trait object at runtime. For example, we could have defined the screen struct using a generic type and a trait bound as in listing 17.6. This restricts us to a screen instance that has a list of components, all type button or all type text field. Monomorphize. Add compile time to use the concrete types. Okay. So basically, it's saying what it's actually advising us is that the if we're gonna have like a single type and we will know the defined type it's gonna hold. So basically, all these lines of codes, what they were trying to say is that there are two. You There's a very powerful language, right? And you will have like two different types of or possibilities of holding a trait, basically, or holding an object of a trait. And if the type of object isn't known and you would like to have it extended, then you would do it as it's actually shown in the first place. But if you do know the type that's going to hold, then you probably want to use it because you're going to have like a lot of compiler optimizations into it. That's what it's actually saying. Because definition will be monomorphized and compile time to use the concrete types. Monomorphized, you can actually understand, and mono means one, morphized like shape, and inferring from the knowledge that you get from the compiler, that it actually makes the zero abstraction that Rust has zero cost abstractions, then it means, or what can I infer from that, is that the compiler will make the optimizations to only specify the right type. I think it would make way more sense if we would understand how compilers work, but I don't want to go that deep. I'm just assuming in here that compilers or the compiled programming language have some sort of type into it, type, like a description of the type that's actually holding. And I think if I'm just making assumptions in here, I'm probably going to be blabbering a lot of garbage, but I think that it's very analog to how an SQL table would work, that you would define the types, but it would work way more at the compiled level. So implementing the trait. Now we'll add some types that implement the draw trait. We'll provide the button type again, actually implementing in UI libraries beyond the scope of this book, so the draw method won't have any useful implementation to its body. To imagine what the implementation might look like, a button struct might have fields for width, height, and label. As shown in listing 17.7. You could actually have define this as an enum as well. Let's have it a struct. But pub struct button. The width, height, and label fields and button will differ from the fields in other components. For example, a text field. No, I don't think so. For example, that might have if we want to draw on the screen, we'll implement a draw trait, but we'll use different code in the draw method to define how to draw the particular type. As Biden has here without the actual UI code, as mentioned, the button type or instance might have an additional implementation block containing methods related to what happens when a user clicks a button. This kind of methods won't apply to types like text field. using our library since implements a select box struct that has width, height, and option fields. Implement the draw trait of the select box type as well, shown in listing 17.8. Dun, dun, dun. Implement draw for select box, the subject of the select box. Our library's user can override their main function to create a screen instance. To the screen instance, they can add a select box and a button. In a box T to become a trait object. They can call the run method on the screen instance, which will call draw on each of the components. So there's implementations. Use select box. Back. Oh, so you see this is now everything makes sense. So everything, so in here, what we're specifying, it's like the screen struct, right? The screen struct in here is holding this trait. And a trait can be implemented by structs. That means that a struct can have different shapes and different lengths, and it does not have like a predefined type. That's why we add the dying keyword, and that's why we also add the box, because the type would be, because box stores the information on the heap, and we do that because we have no idea what's going to be the type at compile time, but the type at runtime. So this is Rust's way for us to specify multiple methods that could be pulled into, let's say, an array. I know in vector it's a different concept, but it's how I can understand it. And it makes a lot of sense. So this is how you start to understand why it is so efficient. Because generally, in dynamically typed languages like JavaScript, Python, PHP, you can't, when you define an array or a list, you can add almost anything to it. So it may have like different types, it may have different, you can even hold functions, you can hold almost anything. But every time, I don't know, and then that's where the runtime environment and even the JIT compiler kicks in. Like, what are the things they do to actually improve? And I'm getting there. So here's the deal. In dynamically typed languages, you don't know what type of information is gonna go through there before it's gonna go through there. So the way that I'm seeing it is that they tend to generalize everything, like every type that let's say the array is going to hold, and they need to create it so it can hold the worst case scenario, because it needs to actually be ready to accept almost anything you can throw at it, and that can become very inefficient because in your code you know what you're going to be working on. They don't know they do not know what is the code that you're going to be creating for. That means that in Rust, it actually gives you all this toolkit or all this tool set, so you can actually create the specified types and the right memory size and the right types you're going to be passing through this array, so it can hold the most efficient set in memory. I'm actually getting it. I think it makes a lot of sense when I put it that way. Makes a lot of sense. So you got the pop struct screen, which is going to be the components, the box line draw, implement screen components. It makes a lot of sense. So it makes a lot of sense. So making it like really short as possible, I would say that for a way for us to see box is to understand that Rust would, we use box and dyn to make the compiler understand that we can accept almost anything through there. And if we don't, then we would enter the monomorphization. It's actually saying, ooh, I'm getting it. I'm getting it. Oh, that was a lot of insight. Oh my goodness. Yeah, let's see. Over the library, the concept being concerned only with messages a value respond to rather than the values concretized in the concept dot typing dynamic type languages. Exactly. If it walks like a dog and quacks like a dog, then it must be a dog. implementation of run and screen listening in 17.5. Run doesn't need to know what the concrete type of each component is. Doesn't check whether a component is an instance of a button or a select box. It's just called the draw method of the component. By specifying a box line draw as the type of the values in the component's vector, we've defined screen to need values that we can call the draw method on. The way that I've seen lists in C Sharp and Java and let's say vectors in Rust and all these strongly typed programming languages is that the concept of interfaces and the concept of traits, the way that I would internalize them is like it's an escape hatch they have. So you can allow multiple types into the function or the method that you are calling. It's a way for you to generalize. I would say that that's one very huge and powerful advantage of dynamically typed languages, even though the con is that they are not as optimized or as efficient as these ones, as Rust or C Sharp. But it's easier, it's less noisy to read and execute. The advantage of using trade options in Rust type system to write code similar to using duck typing is that we never had to check method runtime or worry about getting errors if a value doesn't implement the method, but we call it anyway. Rust won't compile our code if the values don't implement the traits that the trade objects need. Exactly. For example, listing 1710 shows what happens if we try to create a string with a string as a component. Backbox new string, dot dot. Then we will get this error because string doesn't implement the draw trait. This error let us know that we're passing either something to screen we didn't mean to pass, and so should pass a different type or implement the trait objects perform dynamic dispatch. Recall the performance of code using generic section in chapter 10. Our discussion of the monomorphization process performed by a compiler when we use trait bounds and generics. The compiler generates non-generic implementation of function and methods for each concrete type that we use in place generic type router. I do remember about this one. So one of the extremely powerful thing about Rust, I don't know how the inner working about C Sharp works, but when you are creating an interface in C Sharp, and here when you define like generic, like well no we're talking about generics. When when you define a generic in Rust, what it's actually doing, it's that the way that I understand it, it's like some sort of sugar coating everything that we're seeing there, and it's actually making every implementation of the generic go like it would actually create a concrete type for it, and it would pass it through. It's more like a sugar coating. So in fact, like Rust supports generic, but in the inside it doesn't use generics. It's it's actually brilliant. It's brilliant because generics are generally no. In this case, they are always known at compile time. And if you have and now that I'm actually internalizing this concept, if a generic isn't known, if you have a type that isn't known in compile time, then it means that you're probably using a dynamic type, which basically it's like a dynamic trait or a box trait, or no, I mean, sorry for the wrong terms. You're probably going to be storing that object in the stack, no, in the heap, and it should probably be through a box pointer, through a box, and it probably if it's a dynamic trait, if it's a trait, you're probably going to use the dynamic keyword. In other words, is that this is freaking brilliant because you will have the actual concrete types and the dynamic type by itself is a concrete type, a special concrete type of Rust that allows you to write dynamic code. That's what it basically says. And the code that results from monomorphization is doing the static dispatch, which is when the compiler knows what method you're calling at compile time. This is opposed to dynamic dispatch, which is when the compiler can't tell at compile time which method you are calling. In dynamic dispatch cases, the compiler emits code that at runtime will figure out which method to call. When we use trait objects, Rust misuse dynamic dispatch. The compiler doesn't know all the types that might be used with the code that's using trade objects. So it doesn't know which method implemented which type to call. Instead, at runtime, ROS uses the pointers inside the trade object to know which method to call. This lookup incurs a runtime cost that doesn't occur with static dispatch. Of course, it makes a lot of sense. Dynamic dispatch also prevents the compiler from choosing the line of methods code, which in turn prevents optimization. This makes a lot of freaking sense. However, we did get extra flexibility in the code that we wrote in listing 17.5, and we were able to support in listing 17.9. So it is a trade-off to consider. I mean, the way that I'm getting this is that, of course, it makes a lot of sense. So what it's basically saying is that you got two components. It has like two parts. One is the dynamic part, which is when you don't know at compile time. It's more like this traditionally dynamic type languages like Python, JavaScript, PHP that they can hold almost anything because they don't know about it. Because they simplify the code so much, they generalize for everything. This is what happened here. But it is much more efficient. And then you got the actual concrete types, which you know at runtime, at compile time. And even though this is kind of like warning you, however, like this lookups and incurs a runtime cost that doesn't occur with static dispatch. Like this sentence may look like something intimidating, but in practice, most of the time, you do know about the concrete type that you're going to be using. Like you do know the concrete type. The times that you're probably not going to know when you have a concrete type is probably when you're writing a library. But in traditional applications, your backend development and for building startups and the things that we're going to be using, unless your startup or the product you're building is like a tool for other developers to use, you're probably going to fall in this round. Jesus Christ, this is extremely powerful. It's really good. I don't know how many times I've said extremely powerful. That should become me. We went down a rabbit hole. Literally, we went down a rabbit hole. But my question still remains unanswered. Oh my God, it's like 7:59. I'm actually gonna be wrapping everything up. Guys, thank you very much for tuning in, and we'll see you in the next one. Remember to subscribe because we're gonna be continuing. The streams are gonna get better through time. I'm gonna get better at explaining. I'm gonna get better at handling everything, and our goal is to finish the book. Our goal is to finish the book. I know we're going very slow because I'm also documenting my journey and how I learned Rust because Rust is one of the most important programming languages that have come out in the recent few years. I know there are a couple of them that are cooking up, but I think Rust is here to stay and it's going to stay here for a real long time, especially for the way that it handles memory. And for the first time ever, it's being used more in the mainstream to build actual and really important applications. And I think that this is something that we need to learn. It's not, we don't have a lot of options. Now I'm taking like 1 hour from Monday to Friday to learn a little bit about it. And I'm live streaming my journey. So everybody, thanks for tuning in. And I'll talk